A star flies out of the Milky Way at over 1,000 kilometers per second. What are the fastest things in the cosmos, and how do they defy our understanding of physics? By the end of this journey, you will know 50 astonishing facts about the universe's ultimate speed demons. We will encounter stars flung from black holes and particles, moving at the absolute limit of reality itself. How can entire galaxies be racing away from us faster than light? What mysterious force is pulling our own solar system at millions of kilometers per hour? What does it feel like to witness the laws of physics being pushed to their breaking point? That star racing out of our galaxy is astonishingly fast, yet it is still bound by a universal rule that governs every single thing in existence. The absolute speed limit of the cosmos is the speed of light, a blistering 299,792 kilometers per second. Nothing with mass can ever reach this velocity, let alone exceed it. This number is so fundamental to the workings of reality that physicists simply call it c. It is the c in Einstein's most famous equation, and it represents the ultimate traffic law of the universe. This rule is not just about light, it is about causality itself, the principle that cause must always come before effect. If something could travel faster than light, it could theoretically go backwards in time, creating paradoxes that would unravel the very fabric of logic. The speed of light is the constant that ensures the orderly flow of time and information from one point to another. It is the universe's way of maintaining a single, shared reality for all of us. Every single one of the incredible speeds we will explore is measured against this ultimate benchmark, a reminder of the unbreakable laws that even the most powerful cosmic phenomena must obey. Even with that cosmic speed limit firmly in place, some objects come breathtakingly close to breaking it on a purely local scale. The star you heard about at the beginning, the one fleeing our galaxy, is a member of an exclusive class known as hypervelocity stars. These are not your average twinkling points of light. They are cosmic fugitives, flung from the heart of the Milky Way at speeds that can exceed 1,000 kilometers per second. Their story begins with a monster, the supermassive black hole that lurks at our galaxy's very center. When a binary star system, two stars orbiting each other, ventures too close to this gravitational behemoth, a violent celestial dance unfolds. The black hole's immense gravity can capture one star while violently flinging the other away like a slingshot, sending it racing across the galaxy with enough velocity to escape the Milky Way's gravitational pull forever. Astronomers first discovered these runaway stars in the early 2000s, and their existence was a stunning confirmation of theoretical predictions. They are not just curiosities, they serve as vital cosmic probes. By tracing their paths backwards across the sky, scientists can learn about the environment and the immense forces at work around the galactic center, a region otherwise obscured by dense clouds of gas and dust. Each one is a messenger telling the tale of its violent birth and carrying clues about the dark heart of our home galaxy. But the violence that creates hypervelocity stars is nothing compared to the cosmic cataclysm that forges an even faster object. When a massive star explodes in a supernova, its core can collapse into a pulsar. A pulsar is not just a dead star, it is the rapidly spinning, incredibly dense corpse left behind. Imagine taking the mass of our entire sun and crushing it down into a sphere no wider than a city. The result is a neutron star, and when it spins, it becomes a pulsar. The conservation of angular momentum is the key here. Just as an ice skater spins faster when they pull their arms in, the collapsing core of the star spins up to incredible velocities. The Crab pulsar, the remnant of a supernova observed on Earth in the year 1054, spins 30 times every single second. That is a city-sized object rotating faster than a blender blade. These objects possess magnetic fields trillions of times stronger than Earth's. These fields funnel intense beams of radiation out from their magnetic poles. If those beams sweep across Earth, much like the light from a cosmic lighthouse, we detect a regular pulse of energy. This incredible regularity makes pulsars the universe's most precise clocks. Their steady ticks allow scientists to test the laws of gravity, study the fabric of spacetime, and even navigate spacecraft. They are natural laboratories for the most extreme physics, places where matter is squeezed to its absolute limit, and the very rules of nature are pushed to the breaking point. Yet even the furious spin of a pulsar is dwarfed by a far more colossal engine of speed. Deep within the hearts of certain galaxies, supermassive black holes are not just lurking, they are feasting. As immense amounts of gas and dust spiral inward, they form a searing, bright disk of material around the black hole, creating what astronomers call an active galactic nucleus. But the true spectacle happens at the poles. From these points, the black hole can fire out twin beams of plasma, a superheated gas of charged particles stretching across millions of light-years of space. These are relativistic jets, and the matter within them does not merely travel fast, it moves at over 99% of the speed of light. To witness such a jet is to see a structure so vast it could bridge the gap between entire galaxies, all while its constituent particles are moving at the absolute limit of what is physically possible. The energy required to accelerate material on such an unimaginable scale is almost beyond comprehension, channeled by intense magnetic fields and the black hole's own ferocious rotation. These jets are not gentle streams of light. They are the universe's most powerful particle accelerators, carving through intergalactic space and influencing the formation of stars and galaxies in their wake. They stand as a permanent testament to the raw, explosive power that can be unleashed when gravity, at its most extreme, takes control. These relativistic jets are not the only things racing through the void at nearly light speed. Bombarding our planet every second of every day are silent, invisible messengers from across the galaxy, cosmic rays. These are not rays of light at all, but atomic nuclei, the hearts of atoms like hydrogen or iron, stripped of their electrons and accelerated to a staggering fraction of light speed. Each one is a subatomic bullet carrying energies that dwarf anything we can create in our most powerful particle colliders. Their origin story is written in violence, born from the shockwaves of exploding stars. When a supernova blast wave rips through space, it acts like a natural particle accelerator, its turbulent magnetic fields grabbing charged particles and flinging them outward with incomprehensible force. Some of these particles never stop traveling, journeying for millions of years across the galaxy until they finally collide with something like our atmosphere. That collision is where the real mystery begins, when a single high-energy cosmic ray nucleus smashes into an air molecule miles above your head. It creates a spectacular cascade of secondary particles, a silent, invisible fireworks show we call an air shower. Detecting these showers is the only way we can study the primary particles, as the original cosmic rays are annihilated on impact. This indirect method makes pinpointing their exact sources incredibly difficult, as their paths are bent and twisted by the magnetic fields that fill interstellar space. We know they come from somewhere out there, from the most cataclysmic events the universe can muster, but their precise cosmic addresses remain one of astronomy's most enduring puzzles. That enduring puzzle of cosmic rays is tied to the very fabric they travel through. But what if that fabric itself is the source of the most profound speeds in the cosmos? This brings us to a fact that seems to shatter the ultimate rule. The expansion of the universe can indeed exceed the speed of light. This is not a violation of Einstein's laws, but a breathtaking consequence of them. The critical distinction lies in movement through space versus the expansion of space itself. Nothing with mass can ever travel through the cosmos faster than a photon of light. But the empty space between distant galaxies is not empty at all. It is a dynamic stage that is constantly stretching. This is what cosmologists call metric expansion. Think of the universe as a loaf of raisin bread rising in the oven. Each raisin is a galaxy. As the dough expands, the raisins move apart. Two raisins that are close together will only separate slowly. But two raisins on opposite ends of the loaf will be carried apart from each other much faster by the overall expansion of the dough. In our universe, the farther away a galaxy is from us, the more space there is between us to stretch. For galaxies beyond a certain critical distance, known as the Hubble horizon, the cumulative stretching of all that intervening space adds up to a recession velocity that is greater than the speed of light. This means the light those incredibly distant galaxies emit may never, ever reach us. They are disappearing over a cosmic horizon, not because they are moving away through space, but because the river of space itself is carrying them away faster than their light can swim upstream. This is the ultimate speed demon, not an object, but the relentless, accelerating growth of the cosmos we call home. While the expansion of space itself sets the stage for the ultimate cosmic speeds, some of the fastest events are not about travel, but about the instantaneous and violent release of energy. Fast radio bursts are millisecond-long blasts of radio waves that can outshine entire galaxies for the briefest moment. These signals are not from within our own Milky Way. They originate from billions of light years away, crossing unimaginable voids to reach our telescopes. In the span of a single human heartbeat, a fast radio burst can release more energy than our sun will emit over 80 years. The sheer power packed into such a fleeting signal is what makes them one of the most profound puzzles in modern astronomy. The leading suspect for at least some of these bursts is a type of neutron star called a magnetar. Imagine the density of a pulsar, but with a magnetic field 1,000 times more intense. A starquake on the surface of a magnetar, a sudden cracking of its rigid crust, could unleash a cataclysmic rearrangement of its magnetic field, snapping it like a cosmic rubber band and flooding the universe with that telltale flash of radio waves. Yet, the incredible variety and patterns of some bursts have sparked other, more speculative ideas. Could some be the signatures of advanced technologies, the byproduct of immense light sails powering alien spacecraft across the galaxy? While natural explanations are always favored, the very existence of these bursts forces us to confront the limits of our knowledge and consider all possibilities in the vast, dynamic theater of the cosmos. Human engineering has created its own contender in the race for ultimate speed. The Parker Solar Probe, a spacecraft no bigger than a small car, holds the title of the fastest human-made object ever built. It currently races through the inner solar system at speeds exceeding 690,000 kilometers per hour. To achieve such breathtaking velocity, the probe performs a daring cosmic dance with the planet Venus. It does not fly directly toward the Sun. Instead, it uses Venus's gravity as a cosmic brake, carefully adjusting its orbit with each close pass. These gravity assists slow the probe's side-to-side motion, allowing the Sun's immense gravity to pull it into an ever tighter and faster orbit. It is a masterclass in celestial mechanics, using the gravity of one world to fall ever closer to another. The probe's primary mission is as bold as its speed, to solve the long-standing mystery of the solar corona. This is the Sun's wispy outer atmosphere, a halo of plasma visible during a total eclipse. Puzzlingly, the corona is millions of degrees hotter than the Sun's visible surface below it. The Parker Solar Probe flies directly through this superheated region, its revolutionary heat shield enduring temperatures that would vaporize almost any other material. By sampling the solar wind at its source, this champion of human ingenuity is revealing the processes that heat the corona and accelerate charged particles throughout the solar system, protecting our technology-driven civilization from the Sun's volatile temper. Even the fastest cosmic rays are bound by the ultimate speed limit, but what if there were particles born to break the rule? Enter the hypothetical world of tachyons, a class of particles that, by their very definition, always travel faster than light. Unlike everything else in the universe, they would not be able to slow down to the speed of light, let alone go below it. Light speed would be their minimum velocity, not their maximum. This radical idea leads to some truly bizarre consequences rooted in the mathematics of relativity. For a tachyon to fit within Einstein's framework, it would need to possess what physicists call imaginary mass. This does not mean mass that you merely dream up, but a mass value defined by the square root of a negative number, a concept that has no counterpart in our everyday experience of reality. This strange property turns causality on its head. A tachyon could theoretically arrive at its destination before it left its point of origin, effectively traveling backwards in time. This opens the door to paradoxes like the famous grandfather paradox, where you could potentially prevent your own existence. While no tachyon has ever been detected, and most scientists believe they are mathematical curiosities rather than real particles, they remain a powerful tool for thought. They push our understanding of physics to its absolute limits, forcing us to question the very foundations of cause and effect. They are a permanent fixture in science fiction for this very reason, representing a frontier of physics where the normal rules do not apply and the universe becomes a far stranger place than we can possibly imagine. The bizarre concept of tachyons forces us to confront the fundamental rules of our own reality, rules that were confirmed in a spectacular way by the detection of a phenomenon that literally travels at the speed of light. Gravitational waves are ripples in the fabric of spacetime itself, and they move through the cosmos at exactly 299,792 kilometers per second. Albert Einstein first predicted their existence a century ago as a core consequence of his general theory of relativity, envisioning that massive accelerating objects would warp the space around them, sending out these distortions like waves on a pond. For decades, they remained a theoretical ghost, their signals so incredibly faint that Einstein himself doubted we would ever detect them. That all changed on September 14, 2015, when the twin detectors of LIGO, the Laser Interferometer Gravitational Wave Observatory, heard a clear, unmistakable chirp. The source was a cataclysm occurring 1.3 billion light-years away, the final moments of two black holes spiraling into each other and merging into one. In a fraction of a second, an amount of energy equivalent to 3 times the mass of our Sun was converted into pure gravitational waves, shaking the very foundation of the universe. This was not seeing the cosmos, it was listening to it, opening an entirely new sense for astronomy. Since that first detection, we have heard the collisions of neutron stars, events that also produce flashes of light observable by traditional telescopes, allowing us to both see and hear the same cosmic explosion. Each event creates a unique waveform, a cosmic soundtrack that tells us about the masses, spins, and nature of the most mysterious objects in existence. These waves pass through everything unaffected by gas, dust, or stars, bringing us a pristine message from the most violent and energetic event since the dawn of time. The silent symphony of gravitational waves is not the only way the cosmos sends us messengers. In October 2017, astronomers spotted an object tumbling through our solar system that was unlike anything ever seen before. Named Oumuamua, a Hawaiian word for scout, it was the first confirmed visitor from another star system. Its path was a hyperbole, a one-way ticket in and out as it swung around the Sun and began its journey back into interstellar space. But then came the mystery. As Oumuamua sped away, detailed tracking revealed it was not following a path dictated by the Sun's gravity alone. It was accelerating ever so slightly, as if an invisible hand was giving it an extra push. For a simple, inert rock tumbling through the void, this was utterly inexplicable. The most natural explanation scientists reached for was outgassing. When a comet warms up near the Sun, ices on its surface turn directly to gas, jetting away and acting like a natural thruster. The problem was, Oumuamua showed no visible coma, the cloud of gas and dust that always surrounds an active comet. It looked like a bare, rocky asteroid, yet it was behaving like a comet. This paradox sparked a firestorm of scientific debate. Could it be a dusty iceberg, a chunk of solid hydrogen that was venting invisible gas as it was warmed? Or was its shape inferred to be highly elongated like a cigar, playing a role in its strange motion? The lack of a clear, conventional answer opened the door to more speculative ideas. Could Oumuamua have been an ultra-thin light sail, a piece of alien technology propelled by the pressure of starlight itself? While most scientists favor a natural, if unusual, origin, the true nature of this interstellar speedster remains an open case, a permanent reminder that the universe is always capable of surprising us with a new kind of fast-moving mystery. Oumuamua's strange acceleration was a puzzle, but some cosmic objects scream their nature across the void with unmistakable violence. Blazars are the universe's ultimate spotlight beams, supercharged galactic cores aimed directly at us. At the heart of a blazar lies a supermassive black hole, just like in other active galaxies. The difference is one of perspective. Imagine a colossal lighthouse in the distant cosmos, one that fires a pair of energetic jets from its poles. If one of those jets happens to be pointing almost perfectly toward Earth, we are staring directly down the barrel of the universe's most powerful particle cannon. This alignment transforms a merely energetic object into an astronomical superstar, appearing thousands of times brighter in our telescopes than it would from any other angle. The material in these jets is not just hot gas, it is a plasma of subatomic particles accelerated to over 99% of the speed of light. This relativistic motion creates a phenomenon called Doppler boosting, which compresses the light waves and dramatically amplifies the brightness we perceive, like the concentrated sound of a race car as it speeds directly toward you. Because the jets are turbulent and dynamic, blazars do not shine with a steady light. They flicker and flare unpredictably, sometimes doubling in brightness in a matter of hours. This incredible variability makes them some of the most energetic and volatile persistent objects we can observe, cosmic beacons whose light has traveled for billions of years just to deliver a message of raw, unfiltered power. The sheer violence of a blazar's jet is a spectacle of individual escape, but entire star systems can also become cosmic fugitives. NGC 1277 is a supermassive galaxy that is not merely drifting through its cluster, it is fleeing for its life. This colossal island of stars is moving at such a tremendous speed that it is destined to break free from the immense gravitational pull of the Perseus cluster, a family of thousands of galaxies. A single galaxy containing hundreds of billions of stars is on a one-way trip into the lonely void of intercluster space. The forces required to launch an object of this scale are almost beyond imagination. One likely mechanism is a gravitational slingshot, a cosmic billiards game on the grandest scale. If two galaxies pass very close to each other, their mutual gravity can dramatically alter their orbits. In a dense cluster, a third galaxy can act as a gravitational anchor, absorbing some of the orbital energy and flinging one of the others away at a phenomenal speed. Another possibility involves the mysterious hand of dark matter. The invisible halo of dark matter that surrounds a galaxy cluster acts as a gravitational well. A close encounter with another massive object could, in theory, transfer enough energy to a galaxy to literally hurl it up and out of this well, sending it on a permanent exile. These runaway galaxies are more than just curiosities, they are time capsules. Once it escapes the turbulent environment of its cluster, a galaxy like NGC 1277 will stop evolving, its population of stars aging in isolation, preserving a snapshot of its composition from the moment it was violently ejected. They are relics cast adrift from the cosmic communities that forged them, destined to travel the darkness between the clusters forever. Our own star is a constant reminder that immense speed can be born from sudden, violent release. Solar flares are titanic explosions on the sun's surface, and their most powerful eruptions can hurl billions of tons of superheated plasma, a gas of charged particles, directly into space. These events are called coronal mass ejections, and the material they launch can accelerate to speeds of several million kilometers per hour. Imagine the entire mass of a large mountain range like the Rockies being ripped from the sun's surface and flung across the solar system at a fraction of light speed. That is the raw power of a coronal mass ejection. When this billion-ton cloud of charged particles is aimed at Earth, it initiates a high-stakes race across the 93-million-mile gulf of space. The fastest of these ejections can reach our planet in less than a day. The initial impact is a beautiful one as the particles interact with our planet's magnetic field, funneling toward the poles and painting the sky with the shimmering curtains of the aurora. But the beauty masks a serious threat. This incoming wave of solar material carries with it a powerful magnetic field that can induce massive electrical currents in the ground. These geomagnetic storms can overload power grids, causing widespread blackouts, and can fry the delicate electronics of satellites that we rely on for communication, weather forecasting, and navigation. A direct hit from an extreme coronal mass ejection could cripple modern technology on a global scale, a stark reminder that even from 93 million miles away, the sun's incredible speed can reach out and touch our lives in an instant. While solar flares hurl massive clouds of plasma, the sun also emits a far more elusive and faster type of particle. Billions of them are passing through your body at this very moment, ghostly subatomic travelers called neutrinos. Born from the heart of nuclear reactions, these particles are the universe's ultimate speedsters, traveling at velocities so close to the speed of light that for many years, physicists believed they might have no mass at all. Every second, the sun produces a staggering number of them as hydrogen fuses into helium in its core, a process that powers our entire solar system. But the most intense neutrino factories are the cataclysmic deaths of massive stars. When a star goes supernova, an immense burst of neutrinos carries away 99% of the explosion's energy, a flood of ghost particles that races ahead of the visible light. Their near-total lack of interaction with normal matter is what makes them so bizarre. A neutrino can fly directly through a light year of solid lead, a distance of over 9 trillion kilometers, with only a 50% chance of hitting a single atom. This is why they stream unimpeded through planets, stars, and you, leaving no trace of their passage. Detecting something that barely exists requires extraordinary measures like the Super Kamiok and Observatory in Japan, a tank filled with 50,000 tons of ultra-pure water buried deep underground. On the rare occasion a neutrino does collide with an atom in the water, it produces a tiny, telltale flash of light, allowing us to catch a fleeting glimpse of these cosmic phantoms. They are silent witnesses to the most violent events in the cosmos, bringing us information from the hearts of collapsing stars and the core of our sun that no other messenger can deliver. The silent whisper of neutrinos is a constant cosmic background, but one signal from the void was so loud and so strange it was never forgotten. On August 15, 1977, a radio telescope at Ohio State University recorded something extraordinary, a 72-second burst of radio waves so intense that the astronomer who discovered it, Jerry Amon, simply circled the printout data and wrote one word: wow. This was not the random static of the cosmos. It was a powerful, narrowband signal focused on a single frequency, just like what we would expect from an engineered transmitter. Natural cosmic objects tend to emit radio waves across a broad spectrum of frequencies, a chaotic chorus of noise. The wow signal was a pure, clear note, a single instrument playing in an otherwise chaotic orchestra. It came from the direction of the constellation Sagittarius, and then, just as suddenly as it appeared, it vanished, never to be heard again. The signal had to travel at the speed of light for who knows how many years, crossing the unimaginable gulf between the stars, only to wash over our planet for less than 2 minutes. The sheer energy required to produce such a powerful signal across interstellar space points to a source of immense power, far beyond anything humanity was capable of at the time. Despite decades of searching and numerous plausible natural explanations, from a passing comet to a glinting satellite, none have perfectly fit the unique profile of that one brief event. It remains a haunting enigma, a single, brilliant flash in the cosmic dark that continues to fuel the most profound question of all. Are we listening for others, and did one of them for just a moment call out? The haunting silence following the wow signal stands in stark contrast to the cosmic roar of a quasar. These brilliant beacons are the visible heart of a galaxy in its most violent youth, powered by a supermassive black hole feasting on a surrounding disk of gas and dust. But that feast is not a quiet affair. The incredible energy released does not just create light, it forges a hurricane. The accretion disk, that swirling maelstrom of doomed matter, can generate winds of superheated gas and dust that blast outward at a substantial fraction of the speed of light. We are not talking about a gentle breeze, but a supersonic gale powerful enough to reshape an entire galaxy. This is a feedback mechanism of almost unimaginable force. As these relativistic winds scream across space, they slam into the galaxy's reservoirs of cold gas, the very raw material needed to form new stars. The impact is twofold. It can compress some gas clouds, triggering a burst of star formation, but more often, it violently heats and blows the gas clear out of the galaxy entirely. This effectively shuts down the galaxy's star-making factory for eons. A quasar's wind is a cosmic regulatory force, a self-imposed diet that prevents the central black hole from growing too large, too fast, while simultaneously dictating the future evolution of its entire galactic home. The brilliance we see from across the universe is not just the light of consumption, but the signature of this immense galaxy-shaping power. The Parker Solar Probe's breathtaking speed is a modern marvel, but it stands on the shoulders of two earlier pioneers that once held the title. The Helios probes, a pair of spacecraft launched by NASA in partnership with the German Space Agency in the 1970s, were designed for a singular, daring purpose: to fly closer to the Sun than any object before them. Their mission was not to plunge directly into the solar atmosphere, but to orbit our star in an elliptical path that took them deep within the orbit of Mercury. At their closest approach, they skimmed a mere 45 million kilometers from the Sun's fiery surface. This incredibly tight orbit, governed by the relentless pull of solar gravity, is what gave them their incredible velocity. At their fastest, the Helios probes reached speeds of over 250,000 kilometers per hour, a record that stood unchallenged for over 4 decades. While this is less than half the speed of the Parker Solar Probe, it was a monumental achievement for its time, pushing the boundaries of materials science and navigation. Their primary scientific goal was to map the interplanetary medium, the sea of particles and magnetic fields that fills the space between the planets. They were the first to provide detailed measurements of the solar wind, that constant stream of charged particles flowing from the Sun, and they discovered countless microscopic dust particles, the fine grit left over from the formation of the solar system. Every piece of data they beamed back was a vital clue, helping scientists understand the environment that shapes our entire cosmic neighborhood. The Helios missions proved that we could not only survive a close encounter with the Sun, but that we could thrive there, gathering priceless information. They were the essential proof of concept, the daring test flight that showed a solar probe was possible, paving the technological and scientific way for the faster, bolder missions that would follow decades later. The collision of two neutron stars is perhaps the most violent alchemical event in the universe. When these unimaginably dense corpses, each one a city-sized ball of pure neutrons, finally spiral into each other after a cosmic dance lasting millions of years. They do not simply merge quietly. The result is a cataclysm known as a kilonova, an explosion that is briefly 10,000 times brighter than a typical nova. This is not just a flash of light, it is a cosmic foundry in action. For decades, scientists theorized that the heaviest elements in the universe, the gold in your jewelry, the platinum in a catalytic converter, and the uranium that powers reactors, could not be forged in the heart of a regular supernova. The conditions were not quite right. Instead, they were created in the chaotic aftermath of a neutron-star merger. As the two stars tear each other apart, a small but significant fraction of their material, rich with neutrons, is flung outward at speeds approaching a significant fraction of light speed. In this expanding cloud of debris, a frantic process called rapid neutron capture occurs. Atomic nuclei are bombarded by a dense hail of free neutrons, allowing them to grow into the heavy, unstable elements in a matter of seconds. This material then decays, settling into the stable gold and other precious metals we know. The first direct proof of this came in August 2017, when gravitational wave observatories detected the ripples from such a merger, and telescopes around the world and in space saw the corresponding kilonova glow. In that single event, astronomers estimated that an amount of gold equal to several times the mass of our entire planet was synthesized and blasted into the cosmos. Every precious metal on Earth was born from such a spectacular, relativistic explosion, a fleeting but brilliant testament to the destructive beauty of the universe. That gold forged in stellar collisions is a treasure born from motion, but our own galaxy is caught in a far grander and more mysterious current. The Milky Way is not a stationary island in the void. It is a ship racing through the cosmos at an incredible 2 million kilometers per hour. For decades, astronomers were puzzled by this motion, knowing it was too fast to be explained by the pull of any nearby galaxies. The source had to be something colossal, something hidden behind the dense veil of stars and dust in the plane of our own galaxy. This cosmic puppet master is known as the Great Attractor, a gravitational anomaly located about 250 million light-years away in the direction of the Centaurus constellation. It acts like a massive sinkhole in the fabric of spacetime, pulling our entire local group of galaxies along with thousands of others toward its unseen center. The sheer scale of this motion is humbling, a reminder that even a galaxy of hundreds of billions of stars can be tugged across the universe by a force it cannot see. But what could possibly possess enough gravity to command such influence? The original search for the Great Attractor was like trying to find a mountain by looking at the rivers that flow from it. We could see the galaxies all moving in the same direction, but the central peak was obscured by our own galactic backyard. The key to unraveling this mystery lies in the nature of gravity itself on a cosmic scale. The visible stars and gas we detect are only a small fraction of the total mass. The true engine of this immense pull is almost certainly a colossal concentration of dark matter, the invisible scaffolding that shapes the universe. This mysterious substance does not emit or absorb light, but its gravitational pull is undeniable, weaving the galaxies into vast structures called superclusters. The Great Attractor appears to be the dense core of our local supercluster, Laniakea, a Hawaiian word meaning immense heaven. This discovery redefined our cosmic address, showing that the Milky Way is just one of 100,000 galaxies flowing like water droplets down a hill into the same gravitational basin. The quest to fully understand this attractor continues, using radio telescopes that can peer through obscuring dust to map the hidden galaxies at the center of the pull. It is a profound thought that we are all part of a silent, universal river, flowing toward a destination we are only just beginning to see. A magnetar's magnetic field is so powerful it can literally tear the star itself apart. These neutron stars possess magnetic fields 1,000 times stronger than a typical pulsar. creating an environment of almost unimaginable stress. The entire crust of the star, a rigid lattice of atomic nuclei, is under constant strain from these intense magnetic forces. This tension builds until the crust can no longer contain it, cracking violently in what astronomers call a starquake. The energy released in this single event is staggering, greater than the total energy output of our Sun over 100,000 years. All of that power is unleashed in a fraction of a second, a cataclysmic snap that reverberates through the star's entire structure. This sudden rearrangement of the magnetar's rigid surface violently shakes its magnetic field, which is already wound tighter than any spring in nature. The field lines break and reconnect, a process that acts like a cosmic slingshot, accelerating electrons and other particles to velocities incredibly close to the speed of light. As these relativistic particles spiral along the newly reformed magnetic field lines, they emit a brilliant flash of high-energy radiation, a burst of X-rays and gamma rays that can briefly outshine every other source in the galaxy. These are the signals we detect from Earth, fleeting but immensely powerful beacons from a star enduring an almost constant state of magnetic torment. They are not gentle flickers, but the cosmic equivalent of a scream, a testament to a reality where the very fabric of matter is pushed to its absolute breaking point. Even the most meticulously planned journeys can hold subtle surprises. As the Pioneer 10 and Pioneer 11 spacecraft raced toward the edge of our solar system, a ghost seemed to be tugging at them, an unexplained force causing a tiny but persistent deceleration. This was the Pioneer anomaly, a mystery that captivated physicists for decades after its discovery in the 1980s. The spacecraft were billions of kilometers away, speeding toward interstellar space, yet something was ever so gently applying the brakes. The deceleration was minuscule, less than a nanometer per second squared, a force 10 billion times weaker than the gravity we feel on Earth's surface. For years, this tiny signal defied all conventional explanation. Was it a flaw in our understanding of gravity itself, a sign that Einstein's theory needed modification at the vast scales of the solar system? Could it be the gravitational pull of unseen, dark matter clustered near the Sun? Or was it something more exotic, a hint of new physics hiding in the dark, quiet expanse between the planets? The quest to solve the Pioneer anomaly became a masterclass in scientific detective work, forcing researchers to revisit every conceivable variable, from the subtle influence of the solar wind to the gravity of the Kuiper Belt's unknown object. The eventual answer was not found in the darkness of space, but in the gentle glow of warmth. The spacecraft were powered by the steady decay of plutonium in their radioisotope thermoelectric generators, and this process produced heat. That heat radiated away from the spacecraft in all directions, but a small, uneven portion of it was reflected off the back of the spacecraft's large dish antennas. This created a tiny, unintended photon thrust, a gentle push from the light itself. Because the antenna was pointed back toward Earth and the inner solar system, this thermal recoil acted as a constant, faint break, perfectly accounting for the anomalous deceleration. The solution was a profound lesson in humility, a reminder that even the most elegant theories must first be checked against the simple, physical reality of a warm spacecraft in the cold of deep space. Gamma-ray bursts are the cosmos screaming in pure light. For a few fleeting seconds, these events become the brightest things in the observable universe, outshining entire galaxies of stars. They are not gentle flares, but titanic explosions that release more energy than our Sun will across its entire 10 billion-year lifetime, all compressed into a flash you could miss in a blink. The source of this staggering power is a stellar death of unprecedented violence. When the core of a truly massive star collapses, it does not just form a neutron star, it can forge a newborn black hole in an instant. This birth is anything but peaceful. As matter rains down at near light speed into the infant black hole, it triggers an explosion that punches through the star's outer layers. From the poles of this cataclysm, twin relativistic jets erupt, drilling their way out of the dying star. These are not the gentle beams of a lighthouse. They are focused particle cannons of unimaginable intensity, moving at over 99.9% of the speed of light. It is within these jets that the gamma-ray burst itself is born, as internal collisions and turbulent magnetic fields convert the raw kinetic energy of the outflow into a furious blaze of the highest energy photons. If one of these jets is pointed directly at Earth, we witness the full, terrifying spectacle as a long gamma-ray burst. But the death of a massive star is not the only trigger. When two neutron stars, those dense stellar corpses, finally merge in a kilonova, the same physics can unleash a similar, though typically shorter, jet. This creates a short gamma-ray burst, a brilliant flash that signals the creation of heavy elements like gold and platinum. These bursts are so luminous we can detect them from the very edge of the observable universe, making them beacons from the earliest epochs of cosmic time. They are a fleeting, violent signature of the most extreme physics, a reminder that the universe's greatest spectacles are often its most destructive. Our galaxy's 2 million km/h journey is part of a much larger migration. The Milky Way is not traveling alone. It is part of a small family of galaxies called the Local Group, which includes our neighbor Andromeda and dozens of smaller satellite galaxies. This entire cosmic archipelago is not merely drifting, it is falling. We are all being pulled toward an even greater concentration of mass, the Virgo cluster, at a breathtaking speed of several hundred kilometers every second. This motion is a relentless gravitational cascade. Just as the great attractor pulls us, the immense gravity of the Virgo cluster, a dense swarm of over 1,000 galaxies, is reeling in our entire local group from a distance of over 50 million light-years. The invisible hand guiding this grand procession is the cosmic web of dark matter. Picture the universe as a vast, three-dimensional spiderweb with galaxies clinging to the silken threads. Where these threads intersect, they form dense knots, and the Virgo cluster is one such massive knot in our cosmic neighborhood. The gravitational pull from this immense concentration of dark matter, along with all the visible galaxies within it, creates a deep well in spacetime, a slope down which our local group is inexorably sliding. This is not a random drift, it is a fundamental flow, the universe settling into its large-scale structure, with vast voids between these great walls and filaments of galaxies. Our destiny is to eventually merge into this colossal city of stars, a fate that will unfold over billions of years, drawn by a force we cannot see but whose motion we can unmistakably feel. The ghostly pressure of light itself could be the engine for our first journeys to the stars. Solar sails transform sunlight from a passive source of illumination into a tangible force for propulsion. Imagine a spacecraft unfurling a vast, incredibly thin sail, often made of a reflective material like aluminized mylar, stretching for hundreds of meters across. This sail does not catch a wind of air, but a wind of photons, the fundamental particles of light. Although photons have no mass, they do possess momentum, and when they bounce off the reflective surface of the sail, they impart a tiny, continuous push. This force is almost imperceptibly small, weaker than the weight of a butterfly resting on your hand. Yet, in the frictionless vacuum of space, where there is no air resistance to slow things down, that tiny push is constant and cumulative. Day after day, week after week, the spacecraft would gain speed, accelerating with a patience and persistence no chemical rocket can match. It is a slow, steady climb to incredible velocities, a marathon runner rather than a sprinter. Over a long enough journey, such a craft could theoretically reach a substantial fraction of light speed, opening up the possibility of sending probes to nearby star systems within a human lifetime. This is not science fiction. The concept has already been tested. Japan's Ikaro's mission successfully demonstrated solar sail propulsion in interplanetary space, proving that we can indeed sail on sunbeams. But the true potential lies in beaming energy to the sail. Instead of relying solely on the faint pressure of our distant sun, a powerful, focused laser array stationed in orbit could blast the sail with a concentrated beam of light. This would provide a much stronger and more consistent push, accelerating the spacecraft to those dreamlike relativistic speeds far more quickly. A laser-powered light sail could be our first true starship, a silent, fuel-less vessel riding a man-made beam across the unimaginable gulf between the stars. This cosmic cannibalism plays out in a binary system known as the Black Widow pulsar. Here, a rapidly spinning millisecond pulsar is locked in a deadly gravitational embrace with a small, low-mass star. The pulsar, a city-sized object spinning hundreds of times per second, bombards its nearby companion with an unrelenting storm of high-energy radiation and a fierce wind of relativistic particles. This constant assault acts like a cosmic blowtorch, superheating the facing side of the smaller star and literally boiling its material away into space. Stellar gas is ripped from the companion's surface and accelerated to a significant fraction of light speed as it is drawn toward the pulsar's immense gravity. We are witnessing the slow, systematic evaporation of an entire star. This process of mass transfer is actually what spun the pulsar up to its incredible rotational speed in the first place. Over millions of years, gas flowing from the companion star onto the pulsar transferred angular momentum, turning it into a celestial dynamo. Now, having used its partner to reach peak power, the pulsar is actively destroying the very object that created its current state. The Black Widow offers a dramatic, real-time look at the high-speed dynamics of gravitational feeding. The hapless companion star is now just a shadow of its former self, stretched into a teardrop shape and doomed to be completely consumed. This system is a perfect, if terrifying, example of how the most extreme velocities in the universe are often born from the most intimate and destructive of cosmic relationships. This grand flow of galaxies is governed by a simple yet profound cosmic rule. The farther away a galaxy is from us, the faster it appears to be racing into the void. This is not a coincidence, it is a fundamental property of our expanding universe, a relationship known as Hubble's law. The key to understanding this is to think not of galaxies flying through a static space, but of space itself stretching, carrying the galaxies along for the ride. Picture the surface of a partially inflated balloon with a few coins stuck to it. As you blow more air into the balloon, its surface stretches. Every coin moves away from every other coin. Two coins that were close to each other will separate slowly, but two coins on opposite sides of the balloon will rush apart from each other much more rapidly. They are not moving across the surface themselves. The expanding fabric between them is doing all the work. In our universe, each galaxy is like one of those coins. The speed at which a galaxy recedes from us, its recessional velocity, is directly proportional to its distance. A galaxy twice as far away as another is moving away twice as fast. A galaxy 10 times farther away is receding at 10 times the velocity. This steady, predictable drift of galaxies is called the Hubble flow, and it is the primary motion for most of the cosmos. It means that the very coordinates of the universe are in constant, gentle motion, a silent river of space-time on which every galaxy floats. This flow is the reason we see those distant galaxies vanishing over the light-speed horizon, not because they are powerful engines of propulsion, but because the river of space itself is carrying them away. The most energetic particle ever detected struck Earth's atmosphere with the force of a well-thrown baseball, all packed into a single subatomic nucleus. This was the oh my God particle, a cosmic ray of such staggering power that it defies every expectation. Its energy was millions of times greater than anything we can create in the Large Hadron Collider, our most powerful machine. For a single proton to reach such a velocity, it would need to be accelerated by a source of almost unimaginable violence. Yet this creates a profound cosmological puzzle. The universe is not empty, it is filled with the faint afterglow of the Big Bang and a sea of background light from all the stars and galaxies that have ever shone. A proton traveling at such a tremendous fraction of light speed should constantly bump into these low-energy photons. Each collision would act like a tiny break, sapping the particle's energy over millions of light years. By the time an ultra-high-energy cosmic ray reached us from a distant galaxy, it should be reduced to a cosmic crawl. The fact that we detect them at all means they cannot have traveled very far. Their source must be relatively close, cosmically speaking, within our own local supercluster of galaxies. But what nearby cosmic engine possesses the power to launch a single atomic nucleus with more energy than a swinging baseball? The candidates are as terrifying as they are elusive. Could it be an active galactic nucleus with a jet pointed directly at us, or the violent shockwaves from a cluster of merging galaxies? Perhaps the culprit is a supermassive black hole at the heart of a nearby galaxy, flicking particles away with gravitational force. The mystery endures because these events are incredibly rare, and by the time we detect the air shower they create in our atmosphere, the original particle is long gone, its path twisted by interstellar magnetic fields. We are left with the echo of an impossible impact, a cosmic bullet fired from an unknown gun hidden somewhere in our intergalactic neighborhood. The collision of two black holes is a silent, invisible storm of pure gravity. Before they merge, these cosmic titans can whirl around each other in their final moments at velocities approaching half the speed of light. That is over 150,000 kilometers every single second. A frantic orbital dance in the last seconds of a relationship that has lasted for billions of years. It is this incredible final burst of speed that makes them detectable across the universe. As the two black holes accelerate, they churn the very fabric of spacetime around them, sending out ripples that travel at light speed in all directions. These are the gravitational waves first detected by LIGO and Virgo, a discovery that confirmed a century-old prediction and opened an entirely new window on the cosmos. The signal is not a continuous tone, but a rising chirp, a waveform that quickens in both frequency and amplitude as the black holes get closer and faster, culminating in a final, explosive ring as they become one. By reading this cosmic soundtrack, scientists can deduce the masses of the black holes, their spins, and even the distance they traveled from. Each detection is a story of a cataclysm that happened in a galaxy far, far away. Its only evidence a subtle shiver in the lasers and mirrors of detectors here on Earth, a ghostly echo of two darknesses becoming one at nearly the universe's ultimate speed. Even the most straightforward cosmic speed reading can be a clever mirage. A blue shifted quasar presents one of the most beguiling puzzles in astronomy. When we observe the light from a distant object, its color can tell us how it is moving relative to us. If the light is stretched toward the red end of the spectrum, the object is moving away. But if the light is compressed, shifting toward blue, it suggests the object is racing toward us at a tremendous clip. Spotting a blue shifted quasar would therefore imply a cosmic head-on collision course, a beacon from the depths of space hurtling in our direction. Yet, this dramatic interpretation is almost always an illusion. The true culprit is often the warping effect of gravity itself, a phenomenon known as gravitational lensing. Imagine a massive galaxy or cluster of galaxies sitting directly between us and a far more distant quasar. The immense gravity of this foreground object acts like a giant lens, bending the fabric of spacetime and thus the path of the quasar's light. This cosmic trickery can magnify the quasar's image, making it appear brighter, but it can also subtly alter the apparent properties of its light, sometimes mimicking the signature of a blue shift. In other cases, the illusion is created by high-speed gas clouds within the quasar's own system moving in our direction, giving a false local reading of the entire object's trajectory. These rare and deceptive observations serve as a critical lesson. They remind us that the universe is a master of illusion, and that interpreting its high-speed dramas requires more than just a quick glance at the data. Astronomers must become cosmic detectives, carefully untangling the effects of gravity, local motion, and the expansion of space itself to uncover the true velocity and path of these distant, brilliant objects. Decades after their launch, the twin Voyager probes are now silent envoys racing through the interstellar dark. Voyager 1 and Voyager 2 continue their endless journey at speeds exceeding 60,000 kilometers per hour, each carrying a golden record filled with sounds and images from Earth. Their velocity is not the result of a constant engine burn, but a permanent cruise, a testament to the slingshot maneuvers that use the gravity of Jupiter and Saturn to fling them outward. These maneuvers were so precise that they set the probes on trajectories that have carried them beyond the protective bubble of the Sun's influence, a region called the heliopause. Voyager 1 officially crossed this threshold in 2012, with Voyager 2 following in 2018, making them the first human-made objects to enter the space between the stars. They are now sampling the raw galactic material, the winds of particles that flow from other ancient stellar explosions. Think about that for a moment. These machines, built with 1970s technology, are now operating in an environment fundamentally different from anything within our solar system. They are reporting back on the density and magnetic fields of true interstellar space, data we could get no other way. Their power, however, is finite. Their radioisotope thermoelectric generators are slowly decaying, and one by one, their instruments are being turned off to conserve energy. In the coming years, they will fall silent forever, but their mission will continue. They will coast on at their tremendous speed, carrying their time capsules into the cosmic ocean, perhaps to be found one day by another intelligence, or to simply wander the Milky Way as permanent monuments to a curious species on a small blue world. The faintest light in the universe holds a map of our own incredible velocity. This ancient glow is the cosmic microwave background, the cooled remnant of the Big Bang's first flash, and it fills every corner of the cosmos with a near-uniform temperature. Nearly uniform, but not perfectly so. When scientists first mapped this background radiation with exquisite precision, they discovered a mysterious dipole, a directional pattern. One half of the sky appears ever so slightly warmer, while the opposite half appears just a fraction of a degree cooler. This is not a feature of the universe itself, but a signature of our own motion. We are flying through this sea of primordial light so quickly that it creates a cosmic version of the Doppler effect. The radiation in the direction we are heading appears compressed and warmer, just as the sound of an approaching ambulance has a higher pitch. The light from behind us is stretched and cooler, like the receding siren's lower tone. By measuring this temperature difference, astronomers have calculated our solar system's speed relative to this ultimate reference frame. We are racing through the cosmic background at approximately 370 kilometers per second, a staggering 1.3 million kilometers every hour. This is our true velocity through the fabric of the cosmos, a speed compounded from the rotation of our galaxy, its journey toward the great attractor, and the local groups fall into the Virgo cluster. The CMB dipole is our ultimate speedometer, a quiet whisper from the dawn of time that confirms we are anything but stationary, forever passengers on a high-speed voyage through the expanding universe. This subtle chill in the cosmic background radiation is a constant reminder of our own motion, but at the very extremes of speed, motion warps the one thing we consider absolute. Time itself begins to falter. For any object moving at a significant fraction of light speed, time does not pass at the same rate as it does for a stationary observer. This is relativistic time dilation, a direct and mind-bending consequence of Einstein's special theory of relativity. It is not a mechanical error or a trick of perception. It is a fundamental property of the universe, a trade-off between speed and the flow of time. The faster you move through space, the slower your clock ticks relative to someone at rest. This effect is minuscule at everyday speeds, but it becomes profound as you approach the cosmic speed limit. Consider the cosmic rays constantly piercing our atmosphere. Many of these subatomic bullets are traveling at over 99.9% of the speed of light. From our perspective on Earth, a muon, a type of cosmic ray particle, should decay in just 2 millionths of a second, far too quickly to ever reach the ground from the upper atmosphere where it is created. Yet we detect them in abundance at sea level. Why? Because from our frame of reference, the muon's incredibly high speed means its internal clock is running extremely slowly. We see its lifetime stretched out, allowing it to survive the journey to the surface. From the muon's own point of view, its lifetime is normal, but the distance to Earth has been dramatically contracted by its speed, making the trip short enough to complete. This is not just theoretical. We have to account for this effect in our own technology. The Global Positioning System satellites orbiting Earth are moving at about 14,000 kilometers per hour relative to the ground. According to relativity, their onboard atomic clocks should fall behind our terrestrial clocks by about 7 microseconds each day because of their speed. If engineers did not actively correct for this drift, the GPS system would become useless, accumulating errors of kilometers every single day. Your phone's navigation would fail within minutes. Time dilation is a verified reality, a whisper of Einstein's genius that echoes in the silent flight of a cosmic ray and guides us to our next destination. The silent collision of two galaxies offers a ghostly snapshot of dark matter in motion. Astronomers call it the bullet cluster, a system where two galaxy clusters have slammed into each other in one of the most energetic events since the Big Bang. When these titanic structures collided, their individual components reacted in dramatically different ways. The vast clouds of hot gas that fill the space between the galaxies, making up most of the normal, visible matter, were slowed down by a powerful drag force, like two clouds of smoke pushing against each other. This intergalactic plasma piled up in the center of the collision, hot and turbulent, but something else, something invisible, did not slow down at all. By carefully mapping the cluster's gravity using a phenomenon called gravitational lensing, where the mass of the cluster bends the light from more distant galaxies behind it, scientists could trace where the true mass of the system ended up. To their astonishment, the center of gravity for the entire system was not with the visible gas. Two vast clumps of mass had simply sailed right through the collision, carrying on ahead of the stalled gas clouds. This was the dark matter, the invisible scaffolding of the universe, revealing its presence not by glowing, but by its sheer gravitational pull. Because dark matter does not interact with light or with itself through any force except gravity, it felt no friction, no drag. It was like two crowds of ghosts passing through each other in the night, completely unhindered, while the visible residents got tangled up in the streets. The bullet cluster provides perhaps the most direct visual evidence we have for the existence of dark matter. It is a cosmic crash test that demonstrates different components of reality moving at profoundly different speeds, a permanent monument in the sky to the unseen majority that holds our universe together. Rising from the heart of our galaxy like two colossal, ghostly balloons are the Fermi bubbles. These vast structures are not made of glowing gas you can see with an ordinary telescope. They are titanic orbs of gamma rays stretching for 25,000 light-years above and below the galactic plane. To put that in perspective, our entire solar system would be a mere speck lost within one of these immense cosmic bubbles. Their discovery was a complete surprise, announced only in 2010, when scientists analyzing data from the Fermi Gamma Ray Space Telescope noticed this mysterious, symmetrical glow emanating from the galactic center. This was not a gentle, steady light, but the signature of high-energy particles moving at a substantial fraction of the speed of light, slamming into the quieter material of the galactic halo. The source of this ancient violence is almost certainly the sleeping giant at the Milky Way's core, our own supermassive black hole, Sagittarius A star. While it is quiet today, astronomers believe that several million years ago it awoke in a ferocious outburst of activity. As it devoured an enormous clump of gas and dust, it did not just create a bright flare, it likely unleashed a pair of bipolar jets or a gargantuan wind, a hurricane of radiation and plasma that blasted outward from the galactic center. This event would have been a cataclysm of unimaginable scale, a brief but stunningly powerful eruption that punched its way through the surrounding interstellar medium, accelerating particles to near light speed and inflating these giant radioactive bubbles that still linger today. They are a permanent fossil record of our galaxy's most violent temper tantrum, a reminder that even a quiet cosmic neighborhood can have a turbulent and high-speed history. The universe provides its own loopholes to the ultimate speed limit. While objects can never move through space faster than light, the fabric of spacetime itself has no such restriction. This is the radical principle behind the Alcubierre drive, a hypothetical warp engine that bends the rules of physics without technically breaking them. Proposed by physicist Miguel Alcubierre in 1994, this concept is rooted in the solid mathematics of Einstein's general relativity. The idea is not to propel a ship through space, but to manipulate the space around the ship. Imagine a surfer riding a wave. The surfer stays relatively still on the board, but the wave itself carries them forward. An Alcubierre drive would work in a similar way. It would create a warp bubble, a local distortion of spacetime that contracts the fabric of the universe in front of the spacecraft and expands it behind. The ship itself would sit motionless within this bubble, in a flat region of spacetime, completely isolated from the immense tidal forces outside. To an outside observer, the bubble and its contents would appear to be moving at speeds that could vastly exceed the speed of light, all while the passengers experience no acceleration forces and travel without violating any known physical law. The energy required to create and sustain such a warp bubble, however, is the primary reason this remains a thought experiment. Early calculations suggested the need for exotic matter with negative energy density, a substance that may not even exist in our universe. This exotic matter would be required to create the negative pressure needed to expand spacetime behind the craft. The sheer quantity of energy initially proposed was astronomical, equivalent to the mass energy of a planet like Jupiter. More recent studies have suggested ways to reduce the energy requirement, perhaps down to the mass of a small moon or even a large spacecraft, but the fundamental hurdles remain immense. We do not know how to create such a bubble, how to control it once formed, or how to safely collapse it at a destination. For now, the Alcubierre drive is a beautiful piece of mathematical speculation, a testament to human ingenuity in its quest to conquer the stars, and a permanent reminder that the universe's rulebook might be more flexible than we ever dreamed. That ghostly echo from a quasar's violent past is frozen in the depths of space as a celestial phantom known as Hanny's voorwerp, discovered by a schoolteacher named Hanny van Arkel while she was classifying galaxies online. This voorwerp, Dutch for object, appeared as a vast, glowing green cloud of gas with no obvious source of power. It was a cosmic mystery, a glowing specter floating near a seemingly ordinary spiral galaxy. The solution was as brilliant as it was haunting. The cloud is a massive reservoir of gas, but it is not producing its own light. Instead, it is illuminated by a light echo from a cataclysmic event that occurred tens of thousands of years in the past. The neighboring galaxy once hosted a brilliant quasar, a supermassive black hole in a ferocious feeding frenzy, blasting out intense ultraviolet radiation. That light, traveling at its constant cosmic speed, took a long journey. It first washed over the gas cloud, causing it to fluoresce with an eerie green glow, and then it continued on its way into the void. By the time that ancient pulse of light finished its trip to Earth, the quasar itself had already fallen silent, having consumed all the readily available fuel in its vicinity. We are not seeing the quasar itself, but its ghost, a delayed reflection of its former glory. The Voorwerp is a fossil of a high-energy event, a cosmic portrait painted by light that is only now arriving, revealing a chapter in that galaxy's history that is already millions of years over. It is a permanent reminder that what we see in the sky is not necessarily what is, but what was, a universe filled with the luminous ghosts of its own violent past. Deep within the galactic center, a strange object devours its companion and spits out pure antimatter. Known to astronomers as 1E 1740.7-2942, this system has earned a much more dramatic nickname, the Great Annihilator. It is a powerful binary system where a compact object, either a black hole or a neutron star, is locked in a gravitational dance with a normal star. As gas is ripped from the companion, it spirals down into an incredibly hot accretion disk. Here, in the fierce temperatures and powerful magnetic fields surrounding the central object, something extraordinary happens. Pairs of particles and their antimatter counterparts, electrons and positrons, are constantly created from pure energy. But this is not a stable environment. The turbulent dynamics near the event horizon can focus these particles into narrow beams, firing them away at relativistic speeds. We are not talking about a gentle stream of starlight. These are jets of positrons, the antimatter version of an electron. When one of these antimatter particles inevitably encounters a normal electron in the sparse medium of interstellar space, they annihilate each other in a flash of pure energy, releasing 2 gamma-ray photons. This is the ultimate fate of matter, a conversion into pure light, and the Great Annihilator is a cosmic factory where this process is scaled up to a spectacular degree. It demonstrates how the most extreme gravitational environments can become natural laboratories for high-energy physics, creating and launching the very building blocks of antimatter across the galaxy at nearly the speed of light. The perfect ring of Hoag's object is a frozen moment of cosmic violence. This galaxy appears as a nearly flawless circle of brilliant blue young stars surrounding a golden core of ancient suns, with a seemingly empty gap of dark space between them. It is a celestial bullseye, so rare and peculiar that its discovery in 1950 left astronomers with a profound mystery. How does a galaxy arrange itself with such perfect symmetry? The answer lies in speed, not of travel through the void, but of stellar migration. One compelling theory suggests that billions of years ago, a smaller galaxy plunged directly through the heart of what would become Hoag's object. This high-speed collision would have sent immense gravitational shockwaves racing through the galactic disk, violently destabilizing it. Just as a stone dropped into a pond creates ripples moving outward, this impact sent vast waves of gas and stars surging away from the center at tremendous velocities. The outer material was accelerated so fiercely that it broke free from the core's immediate gravitational grasp, collapsing into a new, star-forming ring far from the center. The result is the stunning structure we see today, a galactic core left in peace and a ring of new suns born from the debris of that ancient high-speed encounter. This celestial artifact proves that speed is not only about movement, it is also a sculptor capable of carving the most beautiful and enduring shapes from the chaos of a cosmic crash. The invisible heart of our galaxy was unmasked not by a grand telescope image, but by watching a frantic dance. For decades, astronomers suspected a monster lurked in the galactic core, but the proof came from tracking the orbits of stars like one called S2, a sun many times more massive than our own. S2 does not drift serenely through space. It is whipped around its orbit at a breathtaking speed, accelerating to over 5,000 kilometers per second at its closest approach. That is nearly 2% of the speed of light, a velocity so immense it could cross the Atlantic Ocean in less than a single second. This star is not orbiting a visible object. It is tracing a path dictated by the gravity of something completely dark and unimaginably dense. By meticulously plotting its elliptical orbit over many years, scientists could apply the same laws of gravity that describe the planets orbiting our Sun, but scaled up to a terrifying degree. The calculations revealed that all this frantic motion is caused by a single, invisible point of mass containing about 4 million times the mass of our own Sun. That object is Sagittarius, a star, the supermassive black hole at the center of the Milky Way. The precision of these measurements is staggering, allowing astronomers to not only confirm the black hole's existence, but to test the very limits of Einstein's theory of general relativity in an extreme gravitational environment. We know the mass and location of this cosmic titan not because we can see it, but because we can see the frantic, high-speed waltz of the stars it holds captive. Even our entire observable universe seems caught in a mysterious, sweeping current. Astronomers have detected a strange and controversial large-scale motion they call the dark flow. After mapping the movement of thousands of galaxy clusters, they found a puzzling common drift. These immense structures, each containing hundreds or even thousands of galaxies, are not just moving apart with the Hubble flow. A significant number of them appear to be streaming in the same direction at speeds of several million kilometers per hour. This motion is a profound enigma because it cannot be explained by the gravitational pull of any known object. All the visible matter and even the dark matter we have mapped does not add up to a force strong enough to create this coordinated drift. It is as if a vast, unseen hand is gently tugging on the fabric of our cosmic neighborhood. The most radical explanation proposed is that the dark flow is the gravitational influence of something truly beyond our comprehension, a massive structure that lies outside our observable universe. The very idea challenges a fundamental principle of cosmology, that the universe should be largely uniform and isotropic on the largest scales. If the dark flow is real, it suggests our cosmos is not a self-contained bubble, but merely one patch of a far grander and perhaps infinite reality. The controversy continues as some analyses dispute the statistical significance of the finding, yet the possibility remains haunting. Could we be feeling the gravitational tide from another universe entirely, a neighboring bubble in a vast cosmic ocean, pulling us silently toward an unseen shore? A silent, invisible lighthouse sweeps its beam just 800 light-years away. The Geminga pulsar is one of the brightest objects in the entire gamma-ray sky, yet it remains completely hidden from our eyes. This cosmic powerhouse is the corpse of a massive star that exploded over 300,000 years ago, leaving behind a rapidly spinning neutron star. It completes a full rotation 4 times every second, and as it spins, it whips particle winds to near light speed, creating a pulsar wind nebula that glows with the most energetic form of light. But Geminga is not sitting still. It is racing through the galaxy at over 120 kilometers per second, a velocity so high it acts like a speedboat on a cosmic lake. As it plows through the thin gas of the interstellar medium, its powerful wind slams into this material, creating a vast bow-shaped shock wave that precedes it through space. This bow shock is a cosmic sonic boom, a turbulent frontier where high-energy particles are compressed and heated, marking the pulsar's path across the heavens. We cannot see this structure with optical telescopes, but gamma-ray observatories reveal its magnificent form, a testament to the immense energy being unleashed. Geminga serves as a perfect nearby laboratory for understanding how these spinning stellar corpses inject energy and particles into the galaxy, shaping the very environment between the stars. Far beyond the orbit of Neptune, in the cold, dark reaches where the Sun is just a particularly bright star, lies a vast and silent reservoir. This is the Oort cloud, a spherical shell of icy objects enveloping our solar system at a distance of nearly a light-year. The comets dwelling here are primordial relics, moving with a lethargic grace in the deep freeze of interstellar space. Their orbits are so vast that a single trip around the Sun can take millions of years, their speeds barely a crawl on the cosmic scale. Yet this peaceful existence is an illusion, for these sleeping giants are poised for a sudden and dramatic awakening. All it takes is a subtle gravitational nudge to transform their slow drift into a headlong rush toward the inner solar system. A passing star, even 1 light-years away, can act as a cosmic cue ball, its gravity perturbing the delicate orbital balance of these icy bodies. The immense tidal force of the Milky Way itself, the collective pull of billions of stars as our solar system bobs up and down through the galactic plane, can also provide the necessary push. When this happens, an Oort cloud object is no longer a slow wanderer. It falls inward, pulled by the sun's relentless gravity, gathering speed with every passing million miles. What begins as a gentle drift becomes a breathtaking plunge, accelerating along a highly elliptical path that brings it screaming into the warmth and light of the inner planets. We see these objects as long-period comets, visitors with orbits so long they may only come once in recorded human history. Their spectacular tails a beautiful testament to a violent gravitational shove from the deepest, darkest frontier of our own celestial neighborhood. This immense river of galaxies has a name and a center, a home address for our Milky Way on the grandest scale. We are part of the Laniakea supercluster, a Hawaiian word meaning immense heaven, a name that perfectly captures its staggering scale. Laniakea is not a tightly bound cluster of galaxies, but a vast, sprawling gravitational watershed, a continent in the cosmic web. Within its boundaries, every galaxy group and cluster, including our own local group, is flowing down a gentle, universal slope. Picture a vast, rolling landscape after a heavy rain, with countless droplets of water all trickling downhill toward the same great river valley. In this cosmic analogy, each droplet is an entire galaxy, and the river valley is the gravitational center of Laniakea, the region dominated by the Great Attractor. This motion is relentless and immense. Our entire local group of galaxies is caught in this flow, traveling at hundreds of kilometers per second toward a point in space we cannot directly see, obscured by the dusty plain of our own Milky Way. This is not a journey we will ever complete, for the universe's expansion works against the pull, but it defines our direction within the local cosmos. The map of Laniakea redefines our place in the universe. We are not merely in the Milky Way, which is in the local group, which is part of the Virgo cluster. All of that is just a small neighborhood within the immense, flowing structure of Laniakea, a single thread in a tapestry of 100,000 galaxies, all moving in a silent, coordinated drift toward the same unseen gravitational heart. Human ambition now reaches for the stars not with rockets but with light. The Breakthrough Starshot initiative is a breathtakingly audacious plan to send our first robotic envoys to another star within a generation. Its target is the Alpha Centauri system, our Sun's closest neighbor, a trifecta of stars located just over 4 light-years away. For a traditional chemical rocket, that journey would take tens of thousands of years. Starshot proposes to do it in just 20. The concept revolves around a fleet of gram-scale nanocraft, each one little more than a tiny computer chip attached to a silvery, ultra-thin light sail. These would be the seeds of interstellar travel, launched into Earth orbit first and then met by a different kind of engine entirely. A colossal array of ground-based lasers, spanning perhaps a square kilometer, would combine their beams into a single, phenomenally powerful push of light aimed directly at the sails. For several minutes, this concentrated beam would bathe the delicate sails, their reflective surfaces bouncing the photons to gain momentum. The acceleration would be violent, thousands of times the force of gravity, pressing the tiny crafts forward until they reached an almost unimaginable velocity, 20% of the speed of light. At that pace, they would pass the Moon in mere seconds and fly by Pluto in just a few days. The technological hurdles are as immense as the goal itself. Engineers must design a sail that is both strong enough to withstand the laser's blast and incredibly lightweight, likely only a few atoms thick. The onboard camera, computer, and communication system would need to be shrunk down to the size of a postage stamp, yet be robust enough to survive a 20-year journey through the radiation-filled void of interstellar space. Perhaps the greatest challenge of all is the laser array itself, requiring a level of power and precision that pushes the very boundaries of our engineering. Then there is the final test, the lonely cruise. After the laser shuts off, the tiny probes would coast in the silence, navigating the cosmic dust that could shred them like sand blasting at relativistic speeds. Decades later, if all succeeded, they would scream past the Alpha Centauri system in an hours-long flyby, snapping pictures and gathering data, before beginning the long, slow process of beaming that precious information back to Earth with a laser no more powerful than a single cell phone. The signal would be incredibly faint, requiring a network of telescopes across the globe to have any hope of catching it. Starshot is a dream built on photons, a vision that transforms the gentle pressure of light into the hurricane force needed to cross the interstellar ocean. Long before LIGO heard its first chirp, a silent pair of cosmic clocks provided the first proof that spacetime could ripple. Discovered in 1974, the Hulse-Taylor binary pulsar is a system of two neutron stars locked in a tight, frantic dance. One of them is a pulsar, beaming its lighthouse signal toward Earth with metronomic precision. For decades, astronomers have tracked the timing of these pulses, using them to map the star's orbits with breathtaking accuracy. They found that the two stars are not tracing a fixed, eternal path. Instead, their orbit is slowly, imperceptibly decaying. With each rotation, they spiral a tiny bit closer together, and their orbital speed increases by a minuscule amount. This slow motion in spiral is not caused by friction or any conventional force. It is the direct result of the system losing energy, not as light or heat, but by radiating gravitational waves out into the universe. The energy carried away by these ripples in spacetime is precisely what causes the orbit to shrink. The rate of this orbital decay was measured to an astonishing degree of precision, and it matched the predictions of Einstein's general theory of relativity perfectly. This was not a direct detection of a wave, but something perhaps even more profound, the observation of gravity's long-term effect. A slow but relentless change in velocity driven by the emission of invisible waves. This single binary system provided the first indirect yet undeniable evidence that gravitational radiation was real, setting the stage for the direct detections that would revolutionize astronomy half a century later. That ancient globe bathing the entire cosmos is a faded photograph of creation itself. The cosmic microwave background is the highly red-shifted remnant of the universe's fiery infancy, a direct imprint from a time when everything was smaller, hotter, and unimaginably dense. For nearly 400,000 years after the Big Bang, the universe was a searing plasma, a thick soup of particles and light where photons could not travel freely, constantly bouncing off electrons. Then, in a pivotal moment of cosmic history, the universe expanded and cooled just enough for atoms to form, suddenly clearing the fog. That first flash of light, once brilliant and energetic, began its long journey across an expanding cosmos. The space through which it traveled has been stretching for over 13 billion years, and this relentless expansion has performed a remarkable transformation on the light itself. The fabric of space has stretched the wavelengths of those primordial photons, dragging them from the high-energy, short-wavelength domain of gamma rays all the way down to the low-energy, long-wavelength realm of microwaves. This is the ultimate red shift, a slowing down of light's vibration not because the source is moving away through space, but because the very stage upon which it performs has been stretched to a monumental scale. We are not seeing a distant object, we are seeing a direct consequence of the universe's dynamic history and the incredible speed of its ongoing growth. That faint microwave static is the cooled and faded echo of the universe's first dawn, a permanent testament to the fact that even light itself is not immune to the relentless high-speed expansion of reality. Our own galaxy is on a collision course with a cosmic neighbor. The Andromeda Galaxy, a faint smudge of light in our night sky, is not a distant, tranquil island, but an oncoming titan, racing toward the Milky Way at 110 kilometers every second. This is not a possibility, but an inevitability written in the motion of the stars, a gravitational destiny set in motion billions of years ago. In about 4 billion years, the two galaxies will begin their first close pass, a gravitational tango that will unfold over billions more. Yet, for all the immense speed and scale of this event, you would not need to worry about stars crashing into one another. The spaces between stars are so incomprehensibly vast that the two galaxies will essentially pass through each other, their stars sliding past like phantom ships in an endless dark ocean. The real drama lies not in stellar impacts but in the invisible hand of gravity. As the galaxies swing past each other and then fall back together, their mutual pull will stretch and warp their spiral arms, flinging colossal streams of stars out into the intergalactic void. These tidal tails will be the first visible sign of the merger, luminous scars against the blackness of space. Over eons, the two galaxies will settle into a new, stable form, likely becoming a giant elliptical galaxy, a featureless ball of ancient stars. Our familiar spiral Milky Way will be gone, its beautiful structure erased by this high-speed gravitational dance. The night sky from a surviving planet would be utterly transformed, filled with a brilliant, diffuse glow from countless new stars and the fading embers of the two galactic cores as they finally merge into one. It is the ultimate fate of our home galaxy, a slow-motion crash of almost unimaginable speed and power. A strange, X-shaped object tumbling through the asteroid belt initially fooled astronomers. Designated P/2010-2, it looked for all the world like a comet, complete with a long, dusty tail streaming behind it. But this was no icy visitor from the outer solar system warming in the sun's glow. Telescopic analysis revealed the shocking truth. That tail was not made of vaporizing ice, but of pulverized rock and dust, the shattered remains of a recent catastrophic collision. This was the aftermath of a cosmic car crash, a hypervelocity impact where a smaller asteroid, perhaps only a few meters across, slammed into a larger one at tens of thousands of kilometers per hour. The force of such an impact is beyond any explosion we can conceive. It does not just crack the asteroid, it vaporizes rock at the point of contact, blasting debris outward in an expanding cloud of fine dust and larger fragments. The strange X pattern at the head of the tail was the orbiting wreckage from that instant of destruction, a permanent scar recording a moment of immense violence in the seemingly peaceful void. This ephemeral structure is a ghost, a fast-moving cloud that will gradually disperse over time, its dust swept away by the pressure of sunlight. P/2010-2 gives us a rare and fleeting glimpse into the chaotic construction zone of our solar system, where high-speed collisions are the architects that continually reshape these primitive building blocks, grinding them down or fusing them together in the endless dance of gravity. The ultimate speed demons of the cosmos are far more than a collection of astonishing records. Each one is a natural laboratory, a violent experiment that tests our understanding of reality to its absolute limit. The hypervelocity star flung from the galactic core forces us to map the invisible gravitational fields of our own Milky Way. The frantic spin of a pulsar serves as a cosmic metronome, its steady tick probing the very fabric of spacetime. Even the ghostly push of light on a solar sail confirms the strange, tangible momentum of a photon, a concept that once lived only on a theorist's chalkboard. Every time we observe an object pushing the boundaries of speed, we are handed a new puzzle. Why can a magnet's crust shatter with more energy than our sun emits in 100,000 years? How can a single subatomic particle carry the kinetic energy of a thrown baseball? These are not minor curiosities, they are screaming anomalies that point toward deeper truths. The study of cosmic velocity is a relentless dialogue with the universe itself. We propose a theory, a set of elegant equations that describe how things should work, and then the cosmos responds with a relativistic jet or a fast radio burst, showing us where our beautiful mathematics falls short. This process does not invalidate science, it is science in its purest form, a continuous cycle of prediction, observation, and revolution. Our map of reality is forever being redrawn by these high-speed messengers, each one a key unlocking another door to a deeper, stranger, and more magnificent cosmos than we ever imagined. From the silent, ghostly flight of neutrinos to the violent, star-shattering power of gamma-ray bursts, we have raced across a cosmos defined by motion. We have witnessed stars flung from the galaxy, pulsars spinning faster than kitchen blenders, and entire galaxies swept away on rivers of dark matter. The universe is not a static museum, but a dynamic and often violent arena where speed is the fundamental currency of existence. Every one of these 50 facts reveals a different facet of this high-speed reality, from the absolute limit enforced by a photon to the mind-bending exception where space itself expands faster than light. These are not separate curiosities, but interconnected threads in a single, magnificent tapestry of motion. They force us to constantly revise our understanding of physics, pushing the boundaries of what we thought was possible. Each discovery is a humbling reminder of how much we have yet to learn about the frantic, high-energy dance of the cosmos. Now we want to hear from you. Which of these cosmic speed demons left you the most astonished? Was it the rogue star escaping the galaxy, the phantom push of the Pioneer anomaly, or the sheer power of the oh my god particle? Share your number one fact in the comments below, and if you are hungry for more journeys to the edge of understanding, make sure to subscribe for our next deep dive into the universe's greatest mysteries.